This video is to go through the cathode ray tube experiments. The first page has been given to you, which is the safety, but I've added one more safety rule here, the fact that the glass tubes are fragile and they're under low pressure and therefore they can implode if they're cracked. That's an important safety issue. The other main safety issue is the fact that the induction coil and also the cathode ray tubes can emit X-rays when in operation, so you stand 4 meters away to limit the danger of those, but also the fact the induction coil itself produces about 10,000 volts and therefore you don't touch when it's in operation, and if you do have to touch it and adjust it, you do it with one hand behind your back to avoid current travelling across your heart. So on to the next page. There's just some terminology you need to be aware of, and the first experiment was the gas pressure experiment. We hooked up each tube in turn, and the tubes were getting decreasing pressure, so these were all vacuum tubes, so all under low pressure, but across the rack we had lower and lower pressures of cathode ray tubes, and we hooked up the induction coil to the tubes. One end was hooked up to the anode, which is the positive terminal, one to the cathode, which is the negative terminal. Therefore there's a big electric field across the tube causing a current to flow. This device that makes the high voltage is called an induction coil. It's a special sort of DC transformer. We can talk about how they work later on. That was just hooked up to a 6-volt DC power pack. So what do we see in the experiments? Now all these results and the photographs are actually on Schoolbox, and I strongly recommend you look at them to remind yourselves. We started off at about 3 kilopascals pressure down to 1 pascal of pressure. Normal atmospheric pressure is about 100 kilopascals, so these are quite low pressure. And the main things we saw, and you need to know all these trends, we went from pink streamers to a dark space with a positive column. The dark space got bigger and the positive column became more and more striated as we dropped the pressure, till eventually the dark space took up the whole tube. There was no more positive column, but the glass itself fluoresced, particularly around the anode region. The conclusion of that, well, you've got to summarise the trends you saw as the pressure decreased, and you've got to label that little diagram there. The ones I've put in yellow are the ones I think you actually need to know the names of. The other ones I wouldn't worry about too much, but these are the ones you've got to know what they're called. The next experiment was the experiment to do with Crookes tubes, and the first one, well, the safety is the same for the cathode ray gas tube experiment. The first tube looked at was the Maltese cross tube. You've got to sketch that diagram there. It's very similar, except this time we've got a Maltese cross tube. The anode and cathode are at right angles to each other, and the cross can be in the up position or the down position. And what did we observe in that experiment? Well, first of all, when the cross is down, the whole glass end of the tube fluoresced. When the cross was up though, we saw that dark shadow of the Maltese cross at the end of the tube, showing that the cathode rays themselves couldn't penetrate the metal and they travelled in straight lines, so they only caused fluorescence outside the shadow region of the Maltese cross. And once again, please see the photos and results on Schoolbox for those. There's some results and some conclusions and discussions from that. Travelled in straight lines like light, caused glass to fluoresce, once again like light. Travel from the cathode. We knew that because the glass glowed opposite the cathode and they couldn't penetrate thick metals. That's what they can conclude from that particular experiment. The next experiment was the paddle wheel tube. We set up the experiment as shown, once again very similar, except this time we've got our paddle wheel tube. It's got a slight incline to the glass track. The paddle wheel sits on the track and the anode and cathode are the opposite ends of the top of the paddle wheel. What did we observe? Once again, there's photos and a video on Schoolbox of our experiment, and what we saw was that the paddle wheel rotated away from the cathode, suggesting something was hitting it on the cathode side. It rolled uphill from the cathode to anode, and the phosphors that were painted, special chemicals called phosphors or phosphorescent paints, painted on the paddle wheel, glowed the most brightly opposite the cathode, suggesting something was hitting them from the cathode side. So this green represents the rotation, and the purple represents the rolling up the incline. So what could be concluded from that? First of all, the rotation and movement suggested something was coming out of the cathode. The cathode rays caused the phosphors to glow, which is similar to light's effect on phosphors. The movement of the wheel suggested they carried energy, but also implied they had momentum. They were imparting momentum onto the wheel, which suggested they had mass and were therefore particles. However, scientists, not scientists, who supported the wave model suggest the rotation was due to differential heating effects, not because of transfer of momentum. Electric field tube. Now, we didn't do this at school because we don't have the apparatus for this, but the syllabus just says perform an investigation. So for this part of the experiment, you're going to perform a secondary source investigation. There's a video posted on the Schoolbox under electric field tube. I need you to watch that video to be our results for this particular experiment. But essentially, we just set up a cathode ray tube with electric field plates being supplied by a separate DC voltage inside the tube to make an electric field inside the tube. Now there's two sets of results of this because this is based on history. The first time this was done was by a scientist called Hertz in 1883. He did it with the best technology at the time, but that didn't have quite enough of a vacuum, so there was still a bit of gas inside the tube, and therefore he saw no deflection in electric field situation because the charged particles, or the air that was ionized, actually negated the electric field, and therefore the electrons went straight through, or the cathode rays went straight through without any deflection. But later on, Perrin and Thomson did the same experiment with better technology and a higher vacuum, and therefore they did see deflection towards the positive plate, suggesting they were negatively charged particles. And the conclusion for this is an important conclusion because this is what caused a lot of the controversy. Hertz's experiment suggested they weren't deflected by electric fields and therefore cast doubt over the fact whether they were particles or not, but later on Thomson's verification showed that yes, they were negatively charged particles. Next experiment was the magnetic field tube experiment. We set up the tube, this time a very simple tube, and we held a magnet with a retort stand and clamp outside the tube at different orientations. Now what we observed, you can see on Schoolbox. I'll need you to finish these diagrams. What happened to the cathode rays as they pass through the field coming out of the page and the field going into the page. As you're copying these down, just be careful. These aren't necessarily in the same orientation of tube as on the Schoolbox page. You have to think very carefully about which way the cathode rays are deflecting. And based on the left-hand rule, you should be able to figure out then what charge the cathode rays have based on this experiment. And the results of the experiment strongly suggested they were negatively charged particles, and that couldn't be explained by wave-like phenomena. So the final thing is looking at the controversy, and before Thomson's experiments, which concluded once and for all what these things were, the English scientists generally supported the negatively charged particle model due to their effect on the paddle wheel and the deflection in magnetic fields, while the German scientists were sort of supporting Hertz's experiment that showed they weren't deflected in electric fields, and they supported the wave concept of an electron, mainly because they travelled in straight lines, they weren't deflected in electric fields apparently, and because they caused fluorescence and phosphorescence of glass and paint, and also they caused chemical reactions similar to light. But Thomson's experiment, which demonstrated their deflection of electric fields, it measured their velocity, which was much less than the speed of light, and also calculated their charge to mass ratio, proved once and for all that the cathode rays were negatively charged particles, which he called electrons after someone else's name for negative particles, electrons. And once you've written up all these notes, there is some surfing activities to do after that. So I'm going to post this to a PDF on Schoolbox as well, so you can just go through and write down the notes, but hopefully that's given you a good snapshot of what happened in the experiments.